Hey guys, today we're going to do 1.5 rates of change, squeeze theorem, and limits of compositions and discontinuous functions. Okay. Um, if the bell rings, it's because I'm in the middle of switching to be lunch here. So, and of course, I have to switch the cameras so you're not just looking at my room. There we go. All right. So one thing I want you to do is, as we do this, pay attention to how you need to mark things down, because we have a tendency to do calculations in our head but not tell the reader where we got it, and then we lose points that way. Okay. All right, rates of change. Another meaning for slope is rate of change. We've done that for years, right? In this course, there will be two situations where you will use slopes or rates of change. So let's keep this in mind. We're already getting an introduction to it. So an average rate of change. An average rate of change is a slope between 2 points. Okay, we've done that since 7th grade, I think. And I will then tell you how to write these down to show how much work you have to show. But you can abbreviate average rate of change by AROC. Okay, and then we have the instantaneous rate of change. Okay, this is the new stuff. This is the slope at a single point on a curve or rate of change in a single instant of time. It can be approximated using one or more averages of change and found exactly using calculus. So we can approximate it by using average rate of change for that point, or you'll find out next unit how to do this exactly, to know exactly what the slope is at a single point. It's kind of interesting. Okay, so let's talk about some examples here. So we are given a function x cubed minus 2x squared minus 10. And we're going to find the average rate of change, okay? So first of all, what I want you to make sure you label is that you are finding the average rate of change. And then what you need to do, what you have to do is write in here. Remember, slope is rise over run, y over x, correct? All right, but what you need to use are these numbers. You need to show the greater, not greater, greater, what you're doing with those numbers. You can't just calculate it in your calculator and come up with the answer. They're going to be like, well, where did you find that? So what we're going to do is plug in 3 to our function, subtract the number that we get when we plug in 2, all over our change in x's, which is 3 minus 2. Once you guys do that, this is exactly how you have to write it. You do not have to write that you're plugging 3 in. This is enough information. Now you can use your calculator, and now you can say, well, when I plug in 3, I get -1. When I plug in 2, I get -10, which makes it a +10. All over 3 minus 2 is 1. So when we get our result, we get 9. The average rate of change between 2 and 3 is 9. Now, because we are not in a situation, 9 is a great answer. All right, now I'm going to write a little bit smaller because I'm running out of room. Average rate of change. And again, I'm going to show the person who's grading my paper what I'm doing. I'm plugging in 4 and subtracting the value I get when I plug in 3 all over the change of x. Now, because I'm going under, I don't need to do an error. If I want, I can just do an equal sign. So when I plug in 4, we get 22. When we plug in 3, I get a -1, so +1 all over 1. And I don't want to make the 2 equal signs in one row, so I'm going to put the arrow there, and I get 23. Yeah, hopefully that sounded familiar. Okay, now let's answer this question. Which of these is likely to be a better estimate of the instantaneous rate of change at 2.4? look at your x values. Which of these pairs would give us a closer slope to 2.4? Hopefully you said it was the average rate of change between 2 and 3. Okay, that gives us an estimate. Oops, I did my and symbol backwards. Great. Okay. All right, let's do some other work here. The data in the table shows the mileage from the start of a 4-hour car trip recorded at 1-hour intervals. So see, the intervals are all the same distance. Assume the car continued at in the same straight line. Find the average rate of change. So average rate of change. So 2 points, guys, of the car for the final 2 hours. Well, what are the final 2 hours? Well, we have the average speed, and I'm going to label it as this so that way my grader knows exactly what I'm solving for, average speed. And what I'm doing is the final 2 hours, well, that would be f of 4 minus in the 2 hours, so that would go down to f of 2 all over 4 minus 2. Now, that gives us 250 minus 120 all over 4 minus 2, which equals 65. Now, just to tell you guys, because they actually gave me the y values, I really actually didn't have to do this step. I could have just gone 250 and 120 because they gave me the values. We're up here, they didn't give me -1 and -10. So I had to show where I got those. Hopefully that makes sense. If not, make sure to ask me why. Now this is a situation, so I must have my units. 65 what? Well, this is the average speed. So it's 65 miles per hour. Done. Estimate the instantaneous rate. So we're estimating, guys. So really, we're going to take that average rate of change. And then 1.5. Well, where does 1.5 land in? Right here. So it's easier. Like, could have we done 3 and 0? Yeah, but we're going to be closer to that slope if we get closer and closer, which is 2 and 1. So that means that we get 120 minus 55 all over 2 minus 1. Again, I did not have to put this step in there because they gave me the values. Okay, guys? So that means that the approximation, so the speed at 1.5 hours is approximately, and if we go back and we do that math, we get 65 miles per hour. Now, why did I write what I wrote? Because, yes, I used the average rate of change to get my answer, but it didn't ask me to do the average rate of change. It's how I got my answer. So how makes me rewrite why I'm using the average rate. I'm using the average rate to find the speed at 1.5. Hopefully that makes sense. Okay, during which hour does the data suggest that the car reached the greatest instantaneous speed? So which of these has the greatest change? Well, if you look, our greatest change between any of these values, I just want to make sure something, yeah, is 250 and 180. That's the greatest change, right? That's what, 70? And I think the rest of these are 65. So that means we are the greatest instantaneous is between 3 and 4 hours. I like this here that they're having you play around with the average rate of change and the estimate of instantaneous rate before we get into the definition of it, because you kind of get that mind frame of average rate is using 2 coordinates. Okay. Now, next part of this chapter, or this section, is the squeeze theorem. It's exactly what you think. Squeezing in between, right? Gets smaller and smaller. Now, a lot of this might seem confusing based on the notation, but the truth is I want you to kind of visualize the idea, not so much the notation, okay? So the idea is if we have a function, g of x, and it's in between 2 other functions, okay? 2 other functions. And we're looking at the x does not equal c, but it's containing c, okay? So in other words, like a hole or a jump or something like that, right? If the limit of x approaching c of f of x also equals the limit approaching c of h of x, that means that the limit of x approaching c of g of x is that value, okay? So again, if I have a function that lays in between, and these two have the same limit approaching the same x value, then that is also, we can say, yes, that also happens for g of x because of the squeeze theorem. So what does this actually mean? If a function g is squeezed or sandwiched in between 2 other functions with the same limit, then g approaches the same limit, okay? Now, where can that present itself? Well, here's an example. There's B lunch. The graphs of f of x equals x cubed over 2x and g of x equals negative x cubed over 2x are shown. Find the limit of f of x and g of x as x approaches 0. Okay, well, we want to remember that we need to simplify because otherwise we'd get 0 over 0. So I have limit as x approaches 0 of x squared over 2, right? Because that reduced. Well, when I plug in 0, I get 0 for f of x. Now for g of x, if I plug that in, I get limit as x approaches 0 of negative x squared over 2. And what do I know? When I plug 0 in, I also get 0. Now, remember, the value x can't equal the value, okay? So x cannot equal 0 here because it's a hole. So this is the graph of it, okay? Everybody see what I'm doing? This one's f of x up here, and this is g of x down here, okay? Right here. So the graph of a third function, k of x, is shown along with the 2 other functions. So this right here, let me highlight it. Maybe that will be better. If you see, this is going to be k of x right here. So it is squeezed in between the 2 other functions. Now, since both of these go to 0, that also means that k of x goes to 0. So I can state that the limit of x approaching 0 of k of x equals 0. And now I'm going to say why. Because, or by, the squeeze theorem. Now, I will tell you guys, the squeeze theorem pops up maybe once or twice, but not a lot, okay? So let's practice the idea, and when it does pop up, we'll go over it again, but don't stress yourself out about it. Again, squeezing in between. All right, next one, compositions, and then we're done. So we have 2 graphs here. We're going to use them both, okay? Now it says limit as x approaches 3. The first thing I'm going to do is plug in for f of x and g of x. So if I look at f of x and x is 3, when x is 3, f of x is 3. Because remember, we substitute in first. Plug in 3, so on g of x, look, when x is 3, g of x is 2. Now I can do my math. I get 9 over 3, which is 3. I'm just using both graphs together. Okay, let's try our next one. Remember, go inside out. So the first thing we're going to do is f of 2.5. So at 2.5, f is 3 again. So right here, I'm going to write all my limits because I'm only doing one step at a time. So I got 3. So now I'm doing g of x, but I'm no longer approaching 2.5, right? I'm approaching 3 because that's what happened when I got in here, right? 2.5, it's going 3 from both sides. That's why you switch it. Now if I go 3 over here, I get the value of 2. Okay, this is where our tricky one comes into play, okay? So I'm not going to write limit of 3 like or the 2.5 up here like I did before. I'm going to wait because I got to figure out where x is approaching. So the first thing I'm going to do is check my g of x at 3. At 3, my g of x is 2. But here is what I want to go over. As you can see, guys, right here, g of x is from left and right is both approaching from the bottom, which means kind of that below. But if we were talking about left or right, what would below mean? It would be left. If it was coming from above, it would be to the right. Okay, so this is something that we're going to have to get used to. If we're doing composition of functions, limit composition, and it's both sides are coming from below or above, we're actually on the second function, we're only looking at left or right. If it was coming from both up and down, we're fine. If we're coming both straight across like we did in this one right here, we're fine. But both below means we're going to take the left side. Both above means we're going to take the right side. So now when I look at 2 here, I'm going to look at the left side of it. And if you look, the left side is at the bottom. Well, left side is at -1. Okay? So below 1, the left side. Above, right side. This will take some practice and you will struggle a little bit through it, but it's okay. Make sure you're asking questions as we go through it. Okay, good luck, guys.